Hi, it's Alistair Townsend here, and today I've produced this video to go over the science of learning, how I understand it, and specifically I'm going to look at cognitive overload and how we can reduce its occurrence in our classrooms. Now the first thing I want to do is just give a general overview of the science of learning. So the science of learning is concerned with three general broad areas. The first one is neuroscience, and that's kind of a look into how the brain operates, how it works, and its structure and physiology. Then there is the second part, which is cognitive psychology. So that is the psychology about thinking. Okay, so what's the difference between short-term and long-term memory, and how do we take those memories and make learning occur? So that's cognitive psychology and neuroscience. And then the third area we're looking at here is educational theory. Now, educational theory is quite a broad subject, academic subject, and unfortunately it includes many areas that don't overlap with neuroscience and cognitive psychology, and a lot of educational theory is being developed from observing what's happening in classrooms and then coming up with theories for those. Some of those theories have some link to neuroscience or cognitive psychology, but often they don't. So we develop teaching methods and are guided by this theory in educational practices, and in the past, as I've said, some of those practices have been misguided, or because they haven't linked directly to neuroscience or cognitive psychology. So the science of learning is really taking where these three areas intersect. So we're looking at neuroscience, cognitive psychology, and educational theory, and find where those three things overlap. So where does educational theory overlap and link in with the neuroscience and link in with the cognitive psychology? Because those parts of educational theory are going to have the strongest correlation for improving learning. And that's the general idea behind the science of learning. So in this video specifically, we're going to look at cognitive overload. What is cognitive overload? Well, specifically, cognitive overload is when our memory or our mind has more information than it can deal with at that given time. So our working memory can only deal with a certain amount of pieces of information, and if we overload that, then we have a cognitive overload. So it's really you can link it to both cognitive psychology and to neuroscience here, but it's the consequences of our brains and the limitation of our brains, how our brains collect information from our senses and how we store it. So how do we store the stimuli that comes, and how do we produce concept or schema during our learning? So let's have a look at how our brain can operate. So let's say that we want to, if we're a younger child and we want to learn the word sheep, and we want to associate it with the animal that is a sheep. So for that schema to happen, for that concept or that idea to be linked, the following has to happen. Well, of course, first you have to be able to form the word sheep. So you've got the kind of the sound, the E and P, right? So you can make the word sheep. So those, if we take the word sheep, then there's a wee bit of linguistics here. There's how do we form that word? They all come together to make that word. But that word has to be linked to what we see out there in the paddock. So what we see is we see an oval, it's white, it's got 4 legs, and it's woolly. Okay, so I kind of, that's the stimuli I'm getting, that I'm receiving through my eyes. And now I have to link that concept with this new word that I've learned, which is sheep. Now, what I'm doing here is I'm producing a new schema. Okay, so now I am making a link between the word sheep and this image of a sheep and all the attributes that it has. Now, to make that link happen and to make it strong so that every time that I hear the word sheep, I'm going to see the image sheep and I'm going to know all the ideas around it, I actually need to encounter this multiple times to make the pathway between this bit of stored information that is the sound, okay, that is this phonic information, sound, and this image that I have and attributes of sheep. So I would continue going through and having different learning opportunities or experiences to make stronger connections between those two concepts in my brain. So I'm developing a pathway and I'm making it stronger. And I do that. How do I do that? How do I make these paths easier to travel? Okay, so if we think about cognitive psychology, then we've got this good model for memory. It's called the Baddeley's working memory model. Baddeley came up with this in 1974 and explains how short-term memory processes and temporally holds information. So it has many components within the system. Let's have a look at them. So the first thing that's important in this model are the senses. So what we've got here with the senses, we've got our eyes, our ears, our taste, our touch. And that information that we sense from the outside world is passed into the central executive. Now it acts to supervise and control our attention. What is it that we're going to look at and notice? And it allocates our cognitive resources and it switches between them. So what memory do I need to help? How am I going to deal with the senses that come in and what I already know and put it together to make new ideas? It only has a certain capacity. There's only so much room for us to do that in the brain. So the next part that we have here is the visual sketch pad. Now the visual sketch pad, it processes spatial and visual information. So it stores, manipulates visual images, but not just visual images, but okay, where our feet and our hands are and how we navigate the 3D environment around us. The other most important short-term memory storage, so this visual sketchpad is short-term memory storage, is the phonic loop. Now that handles verbal and auditory information. Now more interesting than that, the verbal and auditory information is linked directly to concepts we've already stored in our brain. So you're going to hear keywords like if I was to say to you sheep, and that image would come up in your brain or you would think about it because it's already linked. Now it holds speech-based information in the ear. It has a finite capacity. Okay, there's only so much of this that we can store at one time, and it's stored in individual pieces, let's say. So the next bit here's our finite capacity here. We might have 5 to 7 different spaces that we can store things in. So once things have then been reconciled in the central executive, the episodic buffer integrates information from the phonic loop, the sketch pad, the long-term memory, and it's like a temporary storage and a system that manipulates and binds all those ideas together in a concept that we can store in our long-term memory. Now the last bit here is the long-term memory. So anything that we have taken in from our senses, so sounds, images, and from the episodic buffer is picked up from our long-term memory and then put those ideas together. Remember the sheep image. So we saw the picture of the sheep, we heard the word sheep, and we took what we already knew about the sheep and brought it into our episodic buffer. We organize it again and make connections between those concepts to come up with a new concept. And that is basically how the Baddeley working memory model explains how we use our senses and our memory to store long-term information. Now, just before we go on, just phonic loop is an interesting thing to think about. So if we think about phonic loop, what does it actually mean, and is a new concept for us possibly, and how do we know what this phonic loop is? Well, we already know something about the word phonic. We know what a megaphone is, a microphone, or a phone that we might hold, a mobile phone, and we get this idea that actually phone has something to do with sound. So phonic is sound, and then the loop, of course, could be a loop in a stitch, a loop in a river, or here is a loop going down around the port in Timaru. Now, this phonic loop is a series of sounds that go around in a loop. And interestingly, when we store information in our phonic loop, we can keep it in there by repeating it or looping it around in there. That's just a wee interesting side note there. Now, what's interesting about the phonic loop is, I alluded to this earlier, but the actual sounds are strongly associated with the concept that that they link to. So the sound sheep is strongly associated to all of those ideas about a sheep. Now, if I want to link two new ideas together, often what I might do is come up with two words that are linking two different concepts together. Now, one of the problems that we have is this information stored in our sonic loop, and when we're a 12 to 17 year old, we might only have 4 to 6 spaces in our phonic loop. So there is actually a variety between people. Some people have less and some people have more, but generally between 4 to 6 or 5 and 7 is how many spaces we have in our phonic loop. Now, any stimuli can be stored in the phonic loop, not just a sound. So actually, because here's how it works. If I observe a cat going through the room, then what my mind sees is a cat, but it actually goes into a sonic buffer, picks up the long-term memory and picks up that phonic cat, that word, and that's stored in the phonic loop, right? So anything that we see that stimulates, that if we're noticing in our room, can fill up a space in the phonic loop. And of course, sounds can fill up a space, a bang, a bell, a word, some music. So our phonic loop is keyed to pick up and store all these wee concepts that we already know, either from our long-term memory or new sounds that we're just hearing that we might associate. Any distraction that we have in the classroom will be stored in our phonic loop and reduce the amount of spaces available for students to work with. The phonic loop acts as a first in, first out basis. So whatever you learned, you first put in that phonic loop, when it gets filled, the first thing we had in there will get popped out. So if you give 9 bits of information to your students, the likelihood is, and they don't get a chance to put that into long-term memory onto paper, they're going to, the first 1, 2, or 3 bits of information are going to be pushed out the back as they hear the new stuff. And we'll have an example of this in a second. So let's have a look at this wee practical activity so we can see how the phonic loop works. So I'm going to call out to you 4 numbers, the 2-digit numbers. You need to store them in your phonic loop. Try not to be distracted by other things. Once I've called out the numbers, I'm going to wait for 5 seconds and then tell you to write them down on a piece of paper. So what you need to do now is you need to go and get a piece of paper and a pen, pause the video, and then remember I'm going to call out 4 different numbers. You're going to wait 5 seconds, you're going to write them down, and then I'll show you the numbers and see if you can get the numbers correct. Okay. So Hope you've unpaused the video. Let's start. 53, 82, 19, 27. Write down the numbers now. Okay, I hope you just had a practical sort of understanding here of how the phonics loop works, right? So you're given 4 numbers that you need to remember. You might keep repeating them through so you don't forget them. You should have been able to remember the 4 numbers that I called out. Let's see whether you got them right. So the numbers were 53, 82, 19, and 27, and you need to get them in the same order. Okay, so you might go, oh, I got that done. My phonics loop works kind of well. That's 4 spaces. Let's have a look at, see what we can do with more spaces. Okay, remember when I said that most students have between 4 to 6 or 4 to 7 spaces? What I'm going to do now is I'm going to repeat the same task, but I'm going to call out 6 numbers. After the 6 numbers have been called out, I'm going to wait for 5 seconds, and then I'm going to ask you to write them down in order. Are we ready? Okay, let's go. 81, 27, 62, 15, 97, 73. Write the numbers down now. Okay, so let's see how we went. So the numbers were 81, 27, 62, 15, 97, and 73. Now, you might have just experienced cognitive overload. You may have got some of these numbers wrong, or you may really have been really challenged to keep all of those 6 numbers in your memory. Even at the end, when I said you can write them down now, you're picking up another bit of information, and it might have chucked out the 81. So this is called cognitive overload, and you may have just experienced it. Okay, let's have another look at some more cognitive overload here. So I'm going to give you 5 seconds to solve the following math problem in your head. Okay, so it's using whatever concepts you already have stored in your long-term memory, and you're going to see if you can solve this problem in your head. Let's go. Okay, let's stop. So did you get the answer? Again, you've most probably experienced cognitive overload. Now here, what the problem with this is, we have the concept 27, okay, the concept multiply, the concept 11, the next concept is the concept of addition, and then 17, and then the concept of multiply again, the concept of 31, and then order of operation. So I need to learn 1, 2, 3, 4, 5, 6, 7, 8. I had to have 8 concepts in my buffer there, okay, episodic buffer. And I needed to manipulate all these things together using my phonics loop to hold some of the information. And look, there isn't a way that I could do this easily. Well, there is a way to do this easily, and I'm going to talk about this, but I can't solve this problem in my head. Oh, and any other noise that you might have had around you, right? That gives 9 things that you might have to store in your episodic buffer and call them back when you need to. So how do we reduce this cognitive overload? So how do we make things that we can pick up new ideas or concepts. We can construct them in our mind without being overloaded. Well, there's a few steps that we can do when we're teaching to make sure that we reduce the cognitive overload. The first one can be scaffolding. That's chunking information into progressive steps. So there isn't an overburden of information at any given time. So chunking information, scaffolding. We can use visual aids. Remember when I talked about you've got this short-term memory, this phonic loop, and you've got this graphic sketch pad? Well, the thing is that actually if your phonic loop is getting close to stored, the graphic sketch pad actually operates independently. So you can actually use visual images of drawing something down. If they're not calling a specific concept, that can be something that adds more space to work with things. So often when we're solving problems, it's really, really good to draw diagrams down for references, because that is part of our memory that we can look at and use as we use these verbal phonic loops. We can simplify instructions. So we provide verbal and written instructions. And they're not too many instructions at one time. We want to limit them to 3 to 4 things. And if it's more than 3 things, then definitely they have to be written down, right, sequentially. So we can follow them. Because otherwise, if we try and remember the instructions as we're trying to do things, we're going to forget them. First in, first out. Number 4, prior knowledge, connection to prior knowledge. If we already know some of the information, if we know a chunk of something, then what we will do is we will take, so if I have 3 concepts already associated in my mind, I will take those 3 concepts in my phonic loop, and my mind will come back with just one word for that, or one idea that will be stored in my phonic loop. So I can replace things I already know associated together with one phonic concept. Minimize distractions. So in our classroom, we need to make sure that we are minimizing the distractions that occur in our classroom, the types of noises that happen, the types of movements that happen, what we have on our walls, or what we are doing as teachers at the front of the class. How are we making sure that we're not actually filling up one of those spaces in the phonic loop? Routines. So routines is a way of minimizing distractions, because a distraction can sometimes be a student being thinking about something that they're unsure about, or they're anxious about, because they're not sure of the routine and what's happening next. So when they're calm, they're going to have more spaces. So just thinking about those types of things in our classroom, we can actually recognize that cognitive overload often occurs in our classrooms because many learners just have 4 spaces available in their phonic loop. Too much information is given out to them, and the phonic loops, the oldest information is discarded and the newest comes in. Unintended information is stored in the phonic loop. So anything that isn't what we want to have the kids work on and associate together is unintended information. It takes up space in our phonic loop, and it slows us down, or it stops us from taking those ideas and constructing a new schema or a new concept. Let's just take a quick sidestep and just look at the neuroscience behind this cognitive psychology. So our brain is made up of a whole billions and billions and billions, hundreds of billions of neurons. They're cells that have multiple connections and connect to each other and send information from one cell to the other through these axons and synapses. Now, synaptic connections, these are the connections between the cells, produce schema or concepts. So do you remember the picture that I had of the sheep earlier, and we had the connections all going towards the picture of the sheep? Well, those kinds of connections happen through neural pathways in our brains. Now, new schemes are produced when 2 or more concepts in our brains find a path of connections through these synaptic pathways. When we make these synaptic pathways between two concepts in our brain, we can produce a new concept. Okay, so the process of learning is taking things that we already know and associating them to each other. And when we look in our brain, what's actually happening, the association is happening as connections between the brain cells, the neurons. Difficult problems become easier when we already know something about the components that make up the problems. That's called scaffolding, and scaffolding is a form of chunking. That is, if I want to learn something complex, I might have to learn something underneath it first to make the more complex thing easier. Right, so let's look at an example of where you may have already done some prior learning and the problem's easier. Now, if you remember the previous math problem I gave you, where you had to multiply two-digit numbers together and then add them to two other two-digit numbers, you experienced cognitive overload. Well, we can reduce that cognitive overload, and here's how we do it. So you have 5 seconds, and here I want you to see if you can solve this problem in your head. So I'm going to give you 5 seconds once you see it to solve the problem, then I'll give the answer. Have a think about whether you got the answer right and why you did. Okay, did you get the answer? The answer is 42. Now, what made this problem easier than the other one? Well, yeah, there's just one digit instead of 2, but that's not the reason why. The reason why is you already learned what 8 times 4 is. So you already have taken the 8, the times, and the 4, and you've brought those 3 concepts together, those 3 parts in your phonic loop, and you can just replace that with the number 32. And you can take the concept of 2 and 5 and multiply and put them together and replace them with the concept of 10. So you have prior information, prior knowledge, and you're using that to take something that you've experienced before and you've made a connection, and you now have a new word for it, which is 2 times 5 is 10, and now you replace it, and so you just have 32 plus 10, and you go, oh, well, that's 42, right? So in this case, you just had to know the order of operation, 32 and 10, 4 things in your phonic loop. Therefore, that made this achievable where the other problem wasn't achievable. So where did your scaffolded learning came from? It came from your early years at school, where you learnt your times tables. So you learnt this concept of 8, right? You knew this concept, you learnt this, and you knew this concept of 4. You were then introduced to the concept of multiplication in 8 times 4. And what you did is you repeated again and again that 8 times 4 equals 32. Maybe you already knew what 32. Maybe you knew it was an even number. Maybe you knew it's how many teeth you would have as an adult. You might have known that it was 2 times 16. You might even associate 32 now, or you might know that it's like 3 10s and a 2, right? But so 32, this number 32, you started to learn your times tables and you linked. You made this linked. Those neurons connected. They made the pathway from one concept, 8 times 4, to another concept, 32. So whenever you see 8 times 4 and 32, you strengthen that pathway. And then you strengthen it some more. So that now any time that you see 8 times 4, you automatically can just swap it out with 32. Especially if you see an operation with it adjoined to it and you see it's a mathematical calculation. So this is our scaffolding, or we've done our prior learning. Now imagine if you didn't know that 8 times 4 was 32 and you had to try, as we did with the double digit numbers, we had to try and keep this 8 in our mind and this 4 in our mind and carry out the operation of times in 8 times 4 when I don't know what it is. And at the same time, while I'm doing this operation, I'm keeping the other bits of information. Okay, the 5 times 2 in there at the same time. Well, that becomes insurmountable. And I can't do the work and I can't learn the new concept because I don't have significant, a correct amount of foundational knowledge, and that is really important, foundational learning. Okay, let's have a look at another math problem. I actually don't want you to solve this in your head, but I want you to think about it, okay? So here it is, 13 times 4 plus 22 times 5. If you were to give that to most year 8, year 9 students, they would find it very hard to do in their mind, or to do as one problem just given to them. So what we actually could do, as well as having prior knowledge, and they might have prior knowledge of what 13 times 4 is, but they most probably don't. So what we would do when we start to get more complex problems like this, that have multiple bits of information that we need to store in our phonics loop, is we can scaffold it to make it easier. Now, what do I mean by scaffolding? Okay, so here's our problem here, and the easiest thing we can do to scaffold that is just get kids to write it down on a piece of paper, right? So what we can then do is we can solve by different components of the problem, and then by doing that we make it easier to solve. So what do I mean by that is we can go, well, let's just take the operation of 13 times 4. So we'll write that down, and then we know that 10 times 4, so I've scaffolded this, and now I'm scaffolding it some more. So 10 times 4 is 40, and 4 times 3 is 12. And then if I add 40 and 12 together, that's 52. Okay, see how this is achievable here? And then the next part I go, well, 22 times 5, let's do that the same way. So we have 22 times 5 is just 20 times 5, which is 100, and 5 times 2, which is 10. 110, and now I can take 110 and 52 and I add them together, and I get the answer of 162. Now you can see here that because we've scaffolded the learning, because we took what was a more complex problem that we could have given to the students, but we broke it down into components, then we can make it so much easier for them to pick up the ideas. Now we're not all going to be doing math problems, but you need to think about anything that you're introducing in your class that is a reasonably complex. You need to make sure that the underlying ideas need to be known well enough so they can associate them together to make the more complex idea. So this is the end of my kind of rambling video about cognitive overload. Where does it come from? How we might solve it? How do we recognize it? Well, and this is just one component of the science of learning. We know that cognitive overload reduces learning. It must. Okay, so anything that's going to overload our ability to store information in our short-term memory, or to take information from our short-term memory and then associate it together in concepts, is going to reduce the learning that we can do. And learning is what we can store, what concepts we can associate together and store in our long-term memory. Remember, it happens because of the limited space in our phonics loop. And the phonics loop does majority of the heavy lifting when it comes to associating new ideas together to make new concepts. We can use the phonics loop more effectively by strategic planning of learning activities in our class. I know what I want you to understand by the end of the lesson, but in order to get there, there are these other small milestones that we have to meet along the way in order for you to not be overloaded and overwhelmed with the stimuli that you're getting, the amount of information you're getting at one time. Two simple methods that we went over to reducing cognitive overload are prior learning, remember the times tables, or the understanding of vocabulary. Okay, if you know what a word means, then you've linked it to an idea or to a concept. And scaffolding. How do we plan the lesson? What are we doing? When we're doing these things, we're following the science of learning. I hope you've found this video interesting, and look out for the rest of the videos I will cover in the series on science of learning.